Greetings, everybody. My name is Lazaros Moysis. I'm from the Aristotle University of Thessaloniki, back in Greece, and today we're going to discuss about the dynamical analysis of a four-dimensional hyperchaotic system with a hyperbolic nonlinearity, sinusoidal nonlinearity, and its application to path planning. So, basically, I'm going to discuss a little bit about chaotic systems. Then we're going to see how a novel chaotic system that we propose can be applied to path planning. And then we're going to discuss future research directions. So let's begin. What is chaos? I'm sure most of you being in the dynamical systems area are familiar with the term. And in mathematics and physics, by chaos, we refer to deterministic systems that showcase an extreme sensitivity to initial conditions and parameter changes. And by that, we mean that a small change in the initial values of the system or in a parameter will yield two completely different solution trajectories. As you can see here, we have a system with two pendulums, and they start from almost identical initial conditions in our simulation. And very quickly, within 2 or 3 seconds, the trajectories of the pendulums quickly diverge from each other. So this is a very simple example of a chaotic system with a very complex behavior. And for chaos, there are mainly 2 research directions. The first direction is their emergence in nature. So a lot of researchers try to understand where do chaos emerges. And there are indications in engineering, in biology, in astronomy, in economy. And the underlying results are that pretty much all physical phenomena have sort of a chaotic nature, because we have indications that chaotic behavior appears pretty much everywhere in nature. And the second research direction is the implementation of chaotic systems in some sort of application related to encryption. And this is because chaotic systems are deterministic in nature and have very high unpredictability. So this makes them very suitable to apply, for example, in text, image, or sound encryption, in secure communications design, or in a robotics design, because they are very easy to simulate, but they are highly unpredictable. So they are very, they can yield very secure encryption designs. And many researchers apply them in that areas, and that's what we do here today. So in our specific paper, what we do is take, for example, a system that was previously proposed by LaNSCom, and we modify it to propose a new system. And the modification is very simple. The system is four-dimensional, and simply we replace this x1, x2 term with a hyperbolic sine term. And also we take this stable term to -1 and change it to -b. So the system has 2 parameters. So we do a simple modification here, and we apply this hyperbolic sine term because there are many indications. A lot of research papers have shown that using this kind of term can easily yield chaotic behavior. And indeed, we have this here. And we will see that the system also behaves, also is hyperchaotic for some values. So we have a simple, potentially hyperchaotic system with 2 parameters. And we saw here that the system also has no equilibria, where when the parameters A and B are non-zero, hence it belongs to the category of systems with hidden attractors. And also we will see that it showcases some crisis phenomena. So to analyze that system dynamically, for example, let's see here its phase portraits for these parameter values right here, which in the next slide we're going to show that indeed for these values the system is hyperchaotic. So for the bifurcation diagram with respect to parameter A, I set beta equals 1, and I see something very nice, that I have a very large region, as you can see here, where the system is indeed chaotic. And you will see that also for some values of the parameter, we have also a second Lyapunov exponent that is positive. So the system is indeed not only chaotic, but hyperchaotic as well. And this is something that I really like for this application, because I really want to have the regions where the system is stably chaotic, So this large region of chaotic behavior is very much desired. And of course, you will see that I have some crisis phenomena where the system abruptly exits chaos as the parameter changes. And again, with respect to the second variable, beta, for alpha equals 0.3, I have the same behavior. There are some small points where the system is hyperchaotic. And more importantly, I have some large period of chaotic behavior, a large range of chaotic behavior. And this is very nice for me in the application because I can choose whatever values I want and the system will indeed be chaotic. Now, for our application, we will consider the problem of chaotic path planning. Now, in this application, what I want to do is to somehow find a method to feed the chaotic values of the system into an autonomous robot so that the robot moves chaotically and unpredictably. And the point of this is to have an autonomous robot, potentially, for example, a camouflaged robot that moves in a manner that an outsider cannot possibly predict. And for example, this is very interesting in applications like, for example, something domestic like floor cleaning, or something like firefighting, or exploration, or patrolling. So let's say you have a patrolling agent that moves chaotically and unpredictably to an area. So an outsider potentially cannot, come inside your area because he doesn't know how your surveilling agent is going to move. So he cannot intrude, So this motion can look unpredictable, but also what we're gonna do potentially is also have it, guarantee a safe exploration of the area eventually. And patrolling, also surveillance cameras is a possible application for this, because you may have a surveillance camera moving around unpredictably. So again, some intruder cannot easily penetrate your safety area. And to apply that, we can choose a very simple method. Here, for example, let's say we have a dynamical robot described by the following differential equations. And to implement the chaotic motion, what I do is I take, for example, the linear and angular velocities of this robot, and I actually feed them the states of the chaotic system. So the angular and vertical velocities of the linear and angular velocities of the system are going to be fed by the states of the chaotic system that I have. And hence, this way, the robot can move chaotically. So let's see, for example, a simulation here for just one robot. I'm sorry if it lags a little bit. You will see that indeed the robot moves completely unpredictably into a given area, and little by little, as it moves, it begins exploring the given area. But at the same time, the robot moves completely unpredictably. See that it works very, very well. And you will see that I applied this simulation for just one robot, but additionally, I can consider, for example, two robots. So let's see the simulation here where I have two robots moving at the same time. And the only thing here that I want to make sure is that the robots do not collide with each other. And I can do so by applying a very simple, mirror mapping technique. So let's say, for example, that I choose a distance that is a safety distance. And the only thing I want to make sure is that if the robots move too close to each other or they move towards an obstacle, I simply take their velocity and I reverse it applying a mirror mapping technique. So yes, I can, for example, replace this velocity with this velocity, and I can make sure that the robots never come close to each other. So you will see, for example, in this graph that indeed the two robots explore the given area. And here, for example, I take the horizontal and vertical coordinate difference of the robots. I choose as a safety distance 2 meters, and indeed they never come too close to each other. Of course, no big deal, I can consider 3 robots as well, and you can see that they begin exploring the area by at the same time avoiding collision. So, I have tried 1 robot, 2 robots, 3 robots. So what about coverage? If I let the robots run for a lot of time, will they eventually cover the whole area? And this is something that I explore into my following slide. I have run a complete simulation, and with respect to simulation time, you will see that in all 3 cases, eventually I go to complete coverage. And what changes, of course, is by using 1 or 2 or 3 robots, is that, of course, eventually the coverage converges much faster when I have a second or a third robot. And of course, this opens up a very interesting question, which is, okay, given a specific space or area, how many robots do I require to cover the whole area? 1, 2, 3, 4, 5. What is the upper bound of the robots that I want to use? And this is a problem for future research studies. So I'm very excited to say that potentially this work can be extended to many different research directions. So for example, we can apply different intelligent techniques or different chaotic systems to improve the coverage performance. Potentially, we can apply this technique to 3D areas using unmanned aerial vehicles, one UAV or maybe multiple UAVs, and see how can they explore the given area fast and efficiently. And of course, there is this huge question of actually implementing this chaotic robot. And there we can solve many different issues that can be related. For example, there is a huge gap between theory and practice that we really need to cover, and bridge. Of course, there is a problem of the smoothness of the motion, the problem of obstacle avoidance, the effect of sampling time on the system, and also the problem of energy efficiency. So, this work I'm very excited to say and very happy to say that it can be moved on to many different research directions, and I'm pretty sure we are going to have a couple more papers surely coming out apart as extensions, of this work. So as a closing remark, I also need to say that I have a special issue with Professor Volos called Recent Advances in Chaotic Systems and Their Security Applications. It's in electronics. If you are interested, feel free to apply. So I want to thank you all for your time. This is who we are. I hope you all stay safe during this time. Please feel free to contact us if you found our work interesting. We are always looking for new research partnerships. So I will be very glad to hear your views. Kind regards from me from Greece. Hope you all stay safe, and we're gonna talk during the discussion time. Thank you very much.